his presentation.
So, Sadi,
Yeah.
hey, good morning, Roman.
Hey, Shashank.
Hey. So before Roman start, can I say just quick words?
Oh, yeah.
Yeah. First of all, thanks all of you for joining in the call. I mean, this great to see all of you here, and thanks to Roman for really taking out the time to provide the talk to the PAC fellows. Roman, I don't know if you're aware about this program, but it's a National Science Foundation program to provide collaborative opportunities between University of Kiel in Germany and all the US institutions. Students from any US institution can apply to go to Kiel and conduct research related to their PhD thesis. A lot of work actually has been done in the area of oxides and functional materials. So materials we are all familiar with, like perovskites and nitrides and carbides of different types, which provide some smart functionalities. So this presentation today is actually pretty matching with what Kiel fellows have been doing, and also it hits a lot of points which actually this program emphasizes. And actually, it's great to have Roman to talk to all of you, because he's very well known in the area of oxides. I've been interacting with him in the area of transparent materials. Probably he's one of the leaders in the area of growing and characterizing these complex oxides, which also happen to be transparent, and has done a lot of work in making variety of materials for energy generation, sensors, actuators, memories, and so on. So I think all the folks on the call and all the PAC fellows who have been at the Kiel and the Kiel students, they will all really like and benefit from Roman's talk. So thanks, Roman, for taking out the time, and it's really great pleasure to have you here. Thank you.
Well, thanks, Shashank, for this kind introduction. And I'm not very familiar with the PAC, but I'm happy to talk about the kind of things that we're doing here at Penn State with regards to material synthesis. And so Sadie told me that I have about half an hour talking about what we've been doing lately. And I decided to entitle the talk Towards Ultimate Control in Complex Oxide and Chalcogenide-Based Materials Grown by Molecular Beam Epitaxy. And so it turns out that the main area of expertise that we have in my group is the growth of thin films, of actually fairly thin films. So we're trying to actually use these bottom-up approach that we have by doing molecular beam epitaxy to rationally design materials at the atomic scale. And the main idea behind this is that we actually destabilize properties so that we can enhance responses to external stimulations. Think about this, that you would like to have very nonlinear responses to an external stimuli. So you would like to position your material right close to, let's say, a phase transition. And this phase transition does not necessarily have to be structurally. This phase transition could be a change in any type of long-range order, whether it's going to be magnetic or whether it's going to be close to a ferroelectric phase transition. So typically the functional materials that we are interested in working with are ferroelectrics and multiferroics. And as Shashank already pointed out, we are also interested in correlated electron systems that typically show electronic phase transitions, and there's a host of material properties that typically emerge in correlated systems such as superconductivity. But then we're not only interested in just doing this for the sake of finding new phenomena and understanding the science better, but we're also trying to make a connection to make it useful to society. So we are also looking for ways to integrate those new materials that we're working with conventional semiconductor platforms. And so really, if you want to capture the mission and the vision of the research group into two sentences, then I would say that our mission is to develop growth methods and materials integration strategies for functional oxide and chalcogenide thin films, because they host a lot of these functional properties for energy harvesting and logic and things like this. And the vision here is to basically do as good of a job as what we've done in the past for semiconductors. So if we would be able to move these types of new functional materials to a quality that would rival the electronic grade quality that we've gotten used to in the materials class of conventional semiconductors, I think we would make a giant leap towards actually utilizing these systems, then also ultimately in devices and in applications. So to give you a little bit of idea of what the capabilities are in the lab, so we have a relatively large MBE cluster at Penn State. And just to give you an idea, we have 2 MBE systems. These are 2 molecular beam epitaxy chambers in which we can evaporate elements from a fusion cells to then grow a film. And so we can do this for the chalcogenides. So everything that has selenium or tellurium in the compound can be grown here in this chalcogenide system. But then we can also grow oxides. In fact, it turns out that the way we started this growth cluster, we first had the oxide system, and then we attached the chalcogenide system. And one of the unique capabilities is that we have an in-vacuum transfer. So we actually can grow oxide films. We can start growing oxide films and then transfer them in vacuum to the chalcogenide system. And then ultimately, we also have the capabilities to do some in situ sputtering. For example, if you're thinking about capping, or if you want to, let's say, deposit ferromagnetic metals, for example, as a contact, then we have also these capabilities for in situ sputtering. Okay, so what I want to do is I want to talk most of the time about the kind of things we're doing on the oxide system. And we predominantly focusing on perovskite oxides. The perovskite structure is shown here on the left. And we are quite intrigued by the perovskite structure because we can fit a diverse set of chemistry into this very same structural motif. And just to give you an idea of what you can put on the A side and the B sides, the A side being shown here as blue and the B side being in the body center of this conventional unit cell, you can see that pretty much the entire periodic table can be put into this crystal structure. And now the interesting thing is that if you are able to grow these materials by a thin film growth technique, there's a few more design knobs that you have access to, which you typically don't have if you grow bulk materials. And the 2 things that we have is that we can strain those films and change the properties that way. But we can also start to use the layering scheme as a design parameter to change the functional properties in these materials. Now, these 2 opportunities come with a challenge. And the challenge is that if you want to utilize these materials, you have to have stoichiometry control. You have to control the defects as you're growing your films. And that's typically, you basically cannot overstate that challenge. Typically, it's been put a little bit under the rock. And this has to do with the typical notion that when you're working with conventional semiconductors, that the interface is the device. This is one of the famous sentences that Herb Kramer said during his Nobel lecture. And it's really true. The interface is the device because that's going to introduce the new functionalities. But really what you need to do is that you need to control your bulk stoichiometry to even be able to study what's going to emerge at the interface. And so for 3.5s, that's relatively easy to do. But for complex oxide materials, this is really going to be a challenge. So really the question always when you're growing these films and when you're growing the heterostructures, like your 101 homework that you have to address is, can you even grow stoichiometric films? And to give you a little bit of an idea of why this is so easy in conventional semiconductors, but it's so hard in oxides, I want to talk for a couple of minutes about the growth kinetics that's taking place in molecular beam epitaxy. And in particular, when I use this example of gallium arsenide, which is probably the most grown material to date in a molecular beam epitaxy system. So the idea is relatively simple. You can see here the conventional unit cell of gallium arsenide, and you can see it consists of gallium and arsenic. So literally all you have to do is you have to supply gallium and arsenic, and typically you do this through thermal evaporation from an effusion cell. And the only thing that you have to do as you're growing those films is you have to make sure that you're hitting this particular thermodynamic condition. So what I'm showing you here is the gas pressure in the system, and that is a measure of the amount of fluxes of arsenic that you're supplying. And you're seeing here two stability lines. And if you use your arsenic flux to be above this line, this stability line, then you're going to ensure that gallium arsenide is going to form. And if you stay below this line, this is the stability line of arsenic, you're going to make sure that all the excess arsenic that cannot get incorporated into your gallium arsenide crystal is going to evaporate. And so this thermodynamic condition that allows for a self-regulated growth is called the growth window. And every time you have a growth window, which you typically have if one of your element is a volatile constituent of your material, you are in game. You can always grow very high quality films by molecular beam epitaxy. And so if you use this idea of this growth kinetics that underpins all of the successful growth of molecular beam epitaxy, you can ask the question now, how's it going to look like when you grow an oxide film? And really the take-home message, without talking about the details here, is that if you map the growth of lead titanate, which also is a perovskite structure, onto the same growth kinetics window, you're going to realize that now it's becoming much, much harder to actually hit your self-regulated growth window. You can see that now the difference in the stability line for the formation of lead titanate down here and making sure that excess lead oxide is going to evaporate, it's going to be much narrower. Okay, so this much smaller growth window turns out is only going to be accessible and only going to be there if one of the constituents of the complex oxide films, in this case lead oxide, is also volatile at the growth conditions or the growth temperatures you're using. Typically here 500 to 700 degrees C. And it turns out that for the complex oxide materials that we are typically interested in, there's only one or two elements that actually deliver on this. The one is bismuth, which is interesting because for the growth of the multifluoric bismuth ferrite, that comes in handy. And it also is true for lead. And that's interesting for growing things like PMNPTs or piezoelectric and ferroelectric materials. All of this works. But now the question is, what is going to happen if you don't have a complex oxide that has a volatile constituent? And for those, you can actually calculate where the self-regulated growth window is going to be. And I'm showing you two examples here that were calculated. One for almost like the godmother of complex oxide materials. This is strontium titanate. And then this one is the growth kinetics for the compound calcium titanate, which is actually the one that gave the name to the perovskite family. So what you can see here is that the typical conditions, and this is in degree C, that I can access by molecular beam epitaxy is this window up here. And you can see is that I'm already pushing towards very high temperatures. And still, I cannot access the self-regulated growth window. I could exit it up here because you can see these lines keep going up. So that means I have to go to really, really high growth temperature. That's technologically not easy to do. Or the other thing that I can do is I can go to much smaller strontium oxide fluxes, which means, and you can see here that this is scaling in orders of magnitude. If I would reduce my growth rate by, let's say, 8 to 9 orders of magnitude, I would re-engage in the self-regulated growth window here shown in gray, and I would have access to a self-regulated growth. Now, both of these are really not a viable strategy to grow these particular complex oxides by molecular beam epitaxy. And what happens now is that the stoichiometry is going to be determined by how much of strontium and titanium flux, or in this case, calcium and titanium flux you're going to supply. And what people have realized, which is shown here, is that this is really, really hard to hit this perfect flux ratio in which you're going to get a stoichiometric composition. Anytime you're deviating from this ideal stoichiometric composition, you're going to see an expansion in your lattice parameter, which is shown here. And you can see that, you typically only have one very specific flux composition in which you can achieve this. That means in all typical deposition techniques for the growth of calcium titanate or strontium titanate, this self-regulated growth window cannot be accessed. And that's really the ultimate challenge if you want to grow high quality complex oxide films. And the solution to this is something that we started working on over 10 years ago. And there's a review article that you can look at. We published this 10 years after making use of a very simple solution. We call this hybrid molecular beam epitaxy. And the idea here is that we're going to take the actual troublemaker in the growth of molecular beam epitaxy of complex oxide, in this case, the titanium. We're going to take this troublemaker titanium and we're going to replace this with a metal organic molecule. Now, it turns out that if you would coordinate titanium with ligands forming a metal organic molecule, the volatility of this molecule is going to be very, very high. And so you can see here that the vapor pressures of this TTIP molecule, TTIP stands for titanium tetraisopropoxide, this vapor pressure is really high. And so the idea is that you would supply, let's say, calcium from a thermal effusion cell. You would inject this titanium containing metal organic precursor through a gas injector. And the volatility of this titanium tetraisopropoxide is going to open that self-regulated growth window. And so this is the hypothesis, this is the idea. And what I'm going to show you in the next couple of slides is that if you apply this hybrid molecular beam epitaxy approach for the growth of titanates, and specifically calcium titanate, you can actually preserve the stoichiometry as you're growing. And so the set of experiments is relatively straightforward. Imagine you want to grow a 20 nanometer thick calcium titanate film. This is challenging. You're going to mount this on a very specific, structurally matching substrate. In this case, we use the LSAT substrate. And what we're going to do now is we're going to supply a fixed flux of calcium from the thermal effusion cell. In this case, we were using a flux of about 2 × 10⁻13 atoms per centimeter squared in second. That gives rise to a growth rate of about 20 nanometers per hour or so. And then what we're going to do in order to get the titanium into the film, because we are targeting to grow calcium titanate, we're going to adjust the flux of this titanium containing metal organic precursor. And so when we are doing this experiment where what we call grow a stoichiometric series, there's a couple of interesting things that we see when we look at the growth using a technique that's called reflection of high energy electron diffraction. And so I'm showing you here the intensity oscillation as we are growing that's typically taken from one of these diffraction spots. And I'm also going to discuss a little bit the type of diffraction images that you see as you grow the film. And so the things that we find is that, for very specific composition or for very specific flux ratios, we get very good oscillations in the intensity of read. And that indicates that the film really grows in a layered by layer fashion. And then the other thing that we see is that we can distinguish different types of surface reconstructions depending on the flux of calcium, which is fixed, and the amount of TTIP that we are supplying as we grow. So you can see that under a very specific condition, which later on turn out to be stoichiometric, we see a 2-by reconstruction as we look at the diffraction image down the 110 azimuth, and we are losing this 2-by reconstruction, this extra peak, as we become too titanium rich, and we change the reconstruction on the surface to a 4-by reconstruction. You can see here 3 side diffraction streaks as we go into 2 calcium rich condition. So really this means that we have a stoichiometric control over our film growth as we grow. And that this is really true, we later on figured out by taking cross-sectional scanning transmission electron microscopy images of the films grown, and we basically saw all of the typical defects that are forming in the film. On a calcium-rich condition, we typically form these stacking faults, these Ruddles and Popper faults. Because of the strain condition, the way we are growing this, they are all oriented out of the plane. For stoichiometric condition, we get basically what we would expect to see for a perovskite film. And then as we go into titanium-rich conditions, you can see these moire structures. They typically come because there's stacking faults, there's the A side that are basically missing, and they detune the position of the TiOX octahedra, and it gives rise to this smeared out image that you would see in scanning transmission electron microscopy. So to make long story short, what I'm showing you here is that we could control the stoichiometry, and what we find is that depending on the flux of this titanium-containing metal organic precursor, we could enter a regime here where we maintained the stoichiometry as measured by the out-of-plane lattice parameter of the film. You can see that despite the fact that we changed the fluxes, we did not change the out-of-plane lattice parameter. And then we confirmed this with energy dispersive X-ray spectroscopy, that really the titanium to calcium ratio did not change for films grown within this growth window. And this really shows that using this hybrid molecular beam epitaxy approach, we can go back to where molecular beam epitaxy works really, really well, which is accessing self-regulated growth windows. Now, does these things properly translate into superior properties in the calcium titanate film? Well, if you want to measure this beyond structural characterization, then certainly you want to do electrical property measurements. Those were strained calcium titanate films. We've done this. The expectation is that calcium titanate films under strain are going to have a ferroelectric ground state at low temperatures. And in fact, we were able to see that at 77 Kelvin, at least for the films that were grown under stoichiometric condition within the growth window, showed very nice polarization curves. We could also trace the transition temperature for the ferroelectric to paraelectric phase transition by looking into the temperature-dependent dielectric constant measurements. You can see here that there's a peak, it's an enhancement in the dielectric constants, typically an indication that there's a phase transition happening. And basically what we did, we tracked this phase transition temperature, this ferroelectric to paraelectric transition temperature, and the signal that we've gotten from second harmonic generation as a function of a growth condition. And what you can see that again, all of the physical properties of the film nicely mapped onto the fact that we had a growth window. You can see that the dielectric and ferroelectric properties did not change throughout the self-regulated growth window, but as soon as you were deviating from these self-regulated stoichiometric growth conditions, we saw a deterioration of the properties. So really, I think what I trying to get across here is that we're able to optimize properties if we are able to access a growth window. And this is also true for oxides. Now, if you take this, you can actually go one step further. So far, I've just limited this discussion to what I would call relatively thick films, but you should be able to scale this down now. And so the second step was trying to grow super lattices, ideally super lattices of two materials, in this case, strontium titanate and calcium titanate. This really hits home this point that we have the same structural motif. We should be able to epitaxially integrate them. And the idea is to basically grow a stack of strontium titanate and calcium titanate, and then repeating this, turns out that given the lattice parameter of strontium titanate and calcium titanate, the strontium titanate would be compressively strained while the calcium titanate would be tensile strained. So we should get some very interesting domain structures in the ferroelectric state. Now, when we started to attempt this, we realized that, like in the case of calcium titanate, where we had a self-regulated growth window, which is shown here, we also find a self-regulated growth window for strontium titanate. You can see here the plot of the out-of-plane lattice parameter as a function of the metal organic flux. And The interesting thing is that the self-regulated growth window here for strontium is somewhat shifted relative to calcium titanate. And so what we did was we just adjusted the strontium and the calcium fluxes to make these two growth windows overlap. And it turns out that this is relatively easy. And as soon as you're able to control the position of these growth windows and you can line them up, you should be able, pretty much for the first time, to grow oxide heterostructures with controlled stoichiometry throughout the entire superlattice stack. And so the idea of what we were really trying to do is to do an A-side modulated co-deposition of the superlattice stack where you supply strontium and this titanium containing metal organic precursor for some time, you know, monolayer or 2 or 5. Then you pause to give the adsorbates on the surface some time to diffuse in the right position. And then you're switching over and you're co-supplying calcium and T-tip. You pause again, you switch back to strontium titanate, pause, switch back to calcium titanate. So in principle, we would expect for reed oscillation to see a layer by layer growth, always n monolayers of whatever, you know, your time is going to be here, of strontium titanate and then n monolayers of calcium titanate. And ultimately, you should end up with a stack that looks like this. This really would be some ultimate control over these designer materials. Now, we've done this because we have such a superior control over the growth conditions. We have grown many of these stacks with superlattices with different repeat unit, all the way from 1 to 10. And what I'm showing you here is the time-dependent reed intensity oscillations. That looks relatively unspectacular. However, when you're zooming in, you can see that, for example, when we're discussing the n equals 10 superlattice, where you have 10 layers of calcium titanate followed by 10 layers of strontium titanate, you can actually see in every growth period these oscillations in reed. And you can literally count how many layers we were putting down to then rest and then put 10 layers of strontium titanate down. And so the exciting part is that this layer by layer control we've achieved for all of these superlattice, irrespective of how many layers we had per strontium titanate or calcium titanate. But then the other exciting thing is that you can see that the intensity oscillation and the trends really look the same at the beginning of the growth and also at the end of the growth, which gives you an idea of how stable this hybrid molecular beam epitaxy approach is. Now, this is not, you know, a very direct look at how these superlattices look like. It would be much nicer to take a cross section and really have a look at it. And you can see that really films and superlattices grown by hybrid molecular beam epitaxy give rise to state-of-the-art superlattice structures. In fact, if you measure the abruptness of these interfaces just by looking at the Z contrast along these lines, you can see that everywhere where we have a calcium titanate, this is the little darker one, you can see that the intensity along the lines of the A site is going to be roughly of the same intensity, while the intensity of the stem contrast for the strontium line is also fairly constant. Sometimes you see a little bit of a deviation. This deviation here for the n equals 5 was not as strong as for the n equals 2 superlattice, and we attribute this to not the precise timing. So there was a little bit of intermixing at those interfaces. In fact, if you do X-ray diffraction, you can very precisely characterize the amount of intermixing. And I'm just flashing here the in-depth X-ray analysis that we've taken on these calcium titanate, strontium titanate superlattices. And so there's a few exciting things here. The most exciting thing is that if you have a very good overall periodicity over the superlattice structure, you would expect to see the satellite peaks in X-ray diffraction that are arising from the superlattice structure. You should see them all the way up to the highest order. And in fact, what we show here is that we achieved this in this complex oxide stack. And the other thing that you can see is that there's a splitting of this nth satellite. And sometimes the splitting is very large. For example, here for the n equals 3. There's also somewhat of a split for n equals 2. This is the one that we just looked at. While in other cases, there's barely any split. For example, n equals 5 or n equals 4 is a very small split. And this split is really coming from the inner mixing that you have at those interfaces. So we were able to see all of these highest order satellite peaks in these super lattices. Okay, so now I have a second part of this, and I'm just gonna forge ahead, except somebody is gonna stop me. And what I wanna talk a little bit about is the growth challenge as you go away from the oxide and you move into the chalcogenides. I talked a lot about, you know, calcium titanate, and you can see calcium, titanium, and oxygen is basically what we are supplying by molecular beam epitaxy. But now let's say we want to switch the element in the group 6. We want to go to chalcogenides, and these are layered compounds. They show topological insulating properties, and they typically come in layered structures. So they're basically researched a lot right now. And so the question is, if you want to grow them by molecular beam epitaxy, what's the problem? And the problem is that these chalcogen elements have very high vapor pressure, while the transition metal elements that you probably want to marry them with have very, very low vapor pressure. And so that makes it very complicated to combine those as a film. And particularly, this very high vapor pressure of the selenium and the tellurium forces you to lower your growth temperature. And that means that you're impeding your growth kinetics. There's going to be barriers, kinetic barriers, surface diffusivity, and even crystallization temperature might be too high compared to the growth temperature that you're applying. So really what you need to do is you have to go all the way away from what you've done in the oxides, where typically growth temperatures on the order of 800 to 900 degrees C, and you have to push it way below 500 degrees C. But this is interesting because if you look into what people are doing right now to replace conventional semiconductors, and you're looking at the trajectory of low power logic devices, if you're focusing on the material here, you can see that in this current area that we are in, that's called hyperscaling area, BEOL, high electron and whole mobility channel materials are interesting. BEOL stands for back end of line. So if you can grow high quality semiconducting materials with thermal budgets below 450 degrees C, that actually becomes very interesting. And among those, and people have worked a lot on tungsten diselenide, moly diselenide, they don't have the greatest mobilities. Among them, platinum diselenide is very interesting because it pushes the envelope of mobility to orders of magnitude that are, you know, typical for silicon as well. So good candidate materials for back end of line integration of semiconducting materials have to be layers that are air stable, that have a high carrier mobility, sufficient band gap, and then ultimately, if you want to build a transistor out of this, a low source drain contact resistance. And platinum diselenide magically meets all of these requirements. Now, if you're trying to grow platinum diselenide, it turns out to be actually really hard. And so what I'm showing you here is some read images that we've taken from the substrate. The substrate we're using is sapphire. And you can see as you carefully increase the growth temperature from 100 to 200, 3, 4, all the way up to 500, you're going to see that you indeed form platinum diselenide, but this read doesn't look that great. You know, there's hazy background indicating that you have an amorphous film. There is at some point some polycrystallinity. You see these lower diffraction rings. Overall, if you're an MBE grower, that's just not good. And then as you increase the temperature, things get better. But at some point, you're losing the selenium because of this very high volatility. Your selenium flux that you are generating is not high enough to maintain platinum diselenide phase. And you're actually ending up with just platinum on the surface. Now, this very initial data was confirmed by ex situ analysis of the films we've grown. You can see an X-ray diffraction, films grown at 100 degrees C, barely have any crystalline phase. It's kind of getting better at 200 and 300 degrees C. There's the formation of a Bragg peak for platinum diselenide. And then as soon as you're overshooting with the temperature, all the selenium are being driven out of the film, and you're left with platinum, with just a platinum film. Now, that means that, and this is also correlating properly with the Raman analysis that we've done, basically means that you have to limit your growth temperature to about 200 to 300 degrees C. We decided to go with 300 degrees C, but you have another trick up in your sleeve. What you can do is that as you've grown the right phase, you can actually do a post-growth salinization anneal, where you basically stop growing, but you're annealing the system, the platinum diselenide, to higher temperature. And when we're doing this, we can see quite an improvement in the read pattern, and we can also see quite an improvement in the crystallinity, both measured by X-ray diffraction here, as well as in Raman spectroscopy. You can see that the specific Raman modes are much pronounced. And so we have a way to grow platinum diselenide, but we have to do it in some sort of a two-step approach, where we have co-deposition at low temperature first, and then a post-growth anneal under selenium flux second. And when we apply the strategy, we can actually start scaling the platinum diselenide thickness all the way from 20 monolayers that we've done here, all the way to actually 1 or 2 monolayers. And we can see how nicely the shift in the EG mode of the Raman is going to higher, to higher frequencies as the film thickness gets lower. And we also see this trend in thickness for this lateral breathing mode. Now, looking at all of those, you can see that there's some sort of formation of platelets here. Interestingly enough, here for these 2 monolayer platinum diselenide and sapphire, the whole AFM, atomic force microscopy morphology, still looks like what we used to see on sapphire. And so we took those films and took a cross-sectional image using scanning transmission electron microscopy. And indeed, what we found was that for the unannealed platinum diselenide films, we have pretty much, to state it politically incorrect, we have pretty much garbage. There's a lot of islands and not very crystalline materials. But as we do the anneal, you can see how a bilayer of platinum diselenide is forming. And this is really not just in one spot. You can take relatively large scans of scanning transmission electron microscopy. You can see that a continuous bilayer of platinum diselenide is really formed. However, it looks a little bit jiggity, and this is simply coming from the fact that these bilayers are not are single crystalline and have the right orientation, but there's a high density of rotational twins formed, and they're just getting stitched together somehow and going to have quite a lot of rotational domain boundaries. So clearly, this is the start, and it requires further improvement, in particular on the crystallinity of these platinum diselenide films. And that just means that we have to do a better job in this post-growth salinization anneal. So this is a little bit of the overview that I wanted to just share with you. So I talked a little bit about new techniques that are necessary to grow functional materials with superior stoichiometric control, in particular oxides. And really what we've done was to push for this hybrid approach, where we are combining molecular beam epitaxy and metal organic chemical vapor deposition. And it has been very successful, not only for the growth of calcium titanate. We've demonstrated this for the growth of various other materials, metals, correlated systems, mud insulators, and things like this. And all of those have shown record electronic properties. And then we have shown that we can generate this growth window, and then ultimately that we are being challenged with a different set of roadblocks for the growth of chalcogenides. What you see here is an AFM image of a submonolayer coverage of platinum diselenide on sapphire. You can see this island formation, which ultimately, if you keep growing and annealing it properly, you can bring this into a 2 monolayer platinum diselenide that's covering the entire substrate. And so with this, I'm going to stop, and I'm going to be happy to ask or answer questions.
Thank you very much, Roman. Let's give a round of applause, guys, to Roman before we start the questions. So go ahead, maybe raise your hand. Maybe that'll make it easier. So there's an icon like a blue color, like raise your hand, and that's why I can say the name. That will make it easier. Rachel, go ahead.
Hi, Dr. Engel-Herbert. Thank you for your talk. I was wondering about the twins that you mentioned, the rotational twins. Are they a challenge for your mobility? And have you seen, does it drastically improve with your salinization anneal?
Okay, so this is an excellent question, and you must have recognized I'm not showing mobility data because I wanted to look good. So it turns out that the mobility that we are getting, the maximum, the theoretical limit of mobility is on the order of 200 centimeters squared per volt seconds. We are hovering about 1 right now. So this looks like a slow start. And what I personally believe is that the reason for this limited mobility is actually coming from these twin boundaries. Yes. So the task is to be able to drive out these twin boundaries, and the idea that we have is actually something that you can see on this slide. You know, we looked at this nucleation behavior of platinum diselenide, and platinum diselenide, if it would be crystalline, should show these typical triangles that we know from the transition metal dichalcogenides. And you can see that none of these islands that we have here has a triangular shape. There's no, you know, zigzag or armchair. Typically, you should see zigzag because lower energy. There's no zigzag boundary here. There's nothing 60 or 120 degree, which tells us that all of these blobs that you see there, we measured them, they are monolayer thick. All of them are pretty much amorphous. So what we have to do is we have to first crystallize these islands before we continue growing. And this is how we hope to dramatically improve the mobility in these layers.
Thank you. Makes sense.
Alexei?
Oh, can you hear me?
Yep, we can.
Okay. Can you just repeat the part about the TTIP, like how the titanium was attached to some other atom?
Yes. So this is something. So this is an idea that goes back to just looking at how people growing complex oxides, and
Right.
if you limit yourself to molecular beam epitaxy and metal organic chemical vapor deposition, and let's say you want to grow strontium titanate, in this case it was calcium titanate, but for strontium titanate it's the same. The pain point of molecular beam epitaxy is actually the titanium. It's really hard to evaporate as a fairly low vapor pressure, and it also reacts with the crucible material. But strontium is no problem. Strontium you evaporate at 450, never gives you any problems. And so in metal organic chemical vapor deposition, it's the exact opposite. The strontium precursors are bulky because strontium is bulky. They don't have good ligands. They don't, have a good thermolysis behavior where they thermally decompose. There's always a lot of byproducts and unintentional carbon incorporation in the film. So the pain point for the growth of MOCVD strontium titanate is actually the strontium metal organic precursor. So we just thought, okay, why don't we take elemental strontium, put it in the fusion cell, which is the MBE part, and we are putting the really well-working metal organic titanium tetraisopropoxide into this gas supply system, and try it this way. For example, it turns out that the chemistry of this titanium tetraisopropoxide is so simple that you can buy like hundreds of grams of titanium tetraisopropoxide from chemical vendors, ready-made for a couple of $100. Actually, cheap. It's basically cheaper than if you would take high purity titanium metal. So this is the idea behind it. It's not that we are synthesizing these metal organic precursors. You can just buy them off the shelf. Is a very conventional product.
Okay. Well, where does the PR go, or what happens to that?
What's the what?
That element, PR.
Oh,
Where does it
PR.
go?
Okay, so this is the abbreviation for propoxy. So basically, what you have is you have titanium. Titanium here in this case is coordinated tetrahedrally by oxygen, and that oxygen is actually part of a propoxy group. See, there's C3. This is the propoxide. You know, the alcohol, the C3H7OH. You basically take the hydrogen away, and you would mount one bond to titanium, and you do this 4 times. And that's literally what people do here. And it's very straightforward. Since the 1950s, people know how to do these metal organic precursors. This particular one is called an alkoxide because you're mounting an alkoxy group. In this case, it's the propoxy to the titanium.
Okay, but I meant like, obviously, like you don't want the rest of that stuff. So what is
Where's it going? That's
yeah.
right. And this is an excellent question. One of the big problems when you do metal organic chemical vapor deposition is that all of these elements that you don't want to have potentially get incorporated into the film. And so we were worried about this for quite some time. And you know, we published on this of what the unintentional carbon contamination in a grown strontium titanate film is, for example. And what we find is that it's below parts per million. So it's actually, if you compare it 1-to-1 to a strontium titanate single crystal, which is easy because you can take a strontium titanate single crystal, you grow a strontium titanate film by hybrid molecular beam epitaxy on it. You do a SIMS analysis, you know, calibrated a secondary ion mass spectroscopy, and you drill through and you look for your carbon contamination. What we found is that if growth temperatures are high enough for us, the carbon contamination of hybrid MBE grown films is actually smaller than what the bulk single crystal is. So it is a concern, and one has to keep track of it. We've done this. Typically, as growth temperatures are high enough, is not going to be your concern right now.
Okay, thank you.
Jamal, go ahead. I think you'll have to unmute Jamal to ask the question.
Thank you, Doctor, for your presentation. I just have a question regarding the calcium flux. What the composition and what the growth temperature that you used?
So growth temperatures, I don't know what the specific growth temperature was. Here you go. The growth temperature we used was 900 degrees C. That's measured by the thermocouple of the substrate holder. And the calcium flux that we used was measured by a quartz crystal microbalance. And we supplied 2 × 10⁻13 atoms per centimeter squared in second. And so if you basically you know, calculate what density you would have for calcium titanate films, that boils down to a growth rate of about 25 or 30 nanometers per hour. And you know, we can actually keep track of the growth rate using these read intensity oscillations. Every time from one maximum to the next maximum is the completion of one entire layer of calcium titanate.
And how did you deal with the evaporation rate of calcium?
So calcium does not evaporate at 900 degrees C fast enough. We did not have any problems with calcium. I think the reason is that calcium stays long enough on the surface, and as soon as it sees a titanium-containing metal organic molecule, they do a chemical reaction forming calcium titanate. And you know, if you leave calcium titanate at 900 degrees C for some time, I think you're going to see, I mean, most oxygen is going to come out, maybe some calcium. but we haven't had any issues with this. You basically kind of calibrate this away because, you know, you fix your calcium flux and you're just asking yourself, how much of the T-tip matching flux do I need to get it right? And so it could be that we're losing some calcium on the way, but this would be really, really hard to track. And we actually don't care. You know, as long as we nail stoichiometry, we're good.
Okay, because although we are working on different project, but we dealt with the evaporation rate and with like different materials, reactive materials. Anyway, thank you very much.
Yeah.
So Roman, have you also investigated this DOE emphasis on metastable materials and tried to synthesize something which was metastable with normal synthesis processes, but the MBE was able to resolve
Yeah,
it?
so we've done this to some extent. So, I mean, one of the things that we're interested in is, for example, stabilizing phases just by epitaxy, where you have two competing phases. The one that everybody gets, you don't get because the free energy that's arising from your, you know, imposed by the epitaxy is going to force it into the actually desired phase. Typically, you know, for phase competition, we have looked a lot into the material system of the vanidates. We were very intrigued by this because lanthanum vanadate is a mud insulator, so it should be an insulator. And strontium vanadate is a metal. So if you position your material, choosing the right composition and the right mixture of lanthanum to strontium, you should be able to sit at a material that shows a strong metal to insulator transition. And so these were the kind of things that we've tried to investigate. Now we are, you know, most emphasis is, you know, implementing the things we've learned from the oxides and implement them in the chalcogenide. So we are very intrigued by the non-conventional superconductors that are more chalcogenide based than, for example, iron selenide. And, you know, we are also pushing hard towards topological materials right now.
Great. I know there's a lot of thermoelectric people on the call, and there's big MBE growers trying to do basically thermoelectrics, because in thermoelectrics, if you can make atomic layer interfaces, then you can do better scattering of phonons.
Yes.
And
yes. I mean, this would be interesting along the lines of an electron crystal phonon glass system. I mean, we have those capabilities in the chalcogenide system. We have a lot of elements in there. They are heavy. And so they would potentially be very interesting for people who are working on thermoelectric materials. And we have the capabilities to layer them and to even, for example, if you think about bismuth selenide, bismuth telluride based thermoelectrics, you know, we can easily integrate them because they have this van der Waals, they have kind of van der Waals materials. We can easily integrate them with, for example, transition metal dichalcogenides, and we can grow stacks to see if there's a way to build an electron crystal phonon glass system.
That sounds great. Any other questions, folks? Okay, if not, then thank you so much, Roman, for taking out the time. This is amazing. I'm pretty sure.
Well, thanks for the invitation.
Yeah. And I'm sure a lot of students and postdocs have benefited. And if you have ever a chance to visit Germany again, please let us know. We'll schedule your visit to University of Kiel. And I'm sure.
Okay, well, traveling is a little hard right now, but I'll get back on this.
Yeah. And I hope.
All right, thank you so much.
Yeah. Thank you so much, everyone. Thank you, Roman. Thanks, Eddie. Thank you very much.